Now we're going to focus exclusively on the really unique part of the IPv6 header, and that's the new format for the source and destination IP addresses. You'll see those here are located in the 8th byte offset from 0 and in the 24th byte offset from 0, with the source IP address coming first and then the destination IP address coming after that. Now, for IPv6 addresses, as we mentioned, the addresses are now 16 bytes instead of 4, so they're 4 times longer, and these are still used to uniquely identify hosts on an IP network. All packets will generally contain a source and destination IP address, or will at least contain that field. That's not to say that one of them can't be all zeros or something really wonky that's invalid, but they will all have those fields to be properly formatted IPv6 packets. Now, the interesting thing about IPv6 addresses, they're actually generally represented not in decimal like an IPv4 address, but actually using hex notation. So you'll see an address like this. So in this case, we have a 16-byte address in hex. So what we have are 4 groups of each group containing 2 bytes apiece. And we see that represented here. Now, the tricky thing about this is these IP addresses are a lot harder to remember. It's very easy to remember 192.168.1.12. It's a lot harder to remember FE 80.0000, so on and so forth. And that's really one of the main drawbacks to functionally using IPv6 is that we have these long, complicated addresses to remember. Now, all that said, that's one of the reasons why DNS is very popular to use, especially in reference to IPv6 addresses. But this is the address structure, and there are a couple different ways we can represent that, though, which I want to talk about here next. Because the IPv6 addresses are a little bit complex and can have a lot of additional padding, there are a few different ways to represent those addresses to make them a little bit easier to digest and process. For instance, one option is collapsing a single grouping of zeros. So let's say we have an address like this, where we have big groupings that are all zeros. You see, we have the first grouping is 1111. The second grouping is 0000. One thing you can do is actually collapse a grouping of zeros. So that's what we did here. And notice in this case, we actually eliminated that second grouping. So now we have 1111, 2 colons, and then 2222. So those 2 colons represent that the thing between those 2 colons are zeros. So we've collapsed that. Now, it's important to note that we've only collapsed the first grouping of zeros. It is actually invalid to collapse multiple groupings of zeros. So if we were to collapse the second and fourth group of zeros, that would actually be an invalid address. You can only do that with a single group. Now, one of the other things you can do is drop leading zeros in an individual grouping. So consider this address, and we have a couple groupings that have leading zeros. So we have one, the fourth grouping is 0333, the fifth grouping is 0044, and the third from last grouping is 0005. So those all have leading zeros within the context of each group. So what you can actually do is collapse those and actually just eliminate those zeros. And notice here in this example, we've actually applied the previous thing we talked about, collapsing a single group of zeros as well. So we've gotten rid of the second grouping altogether. We see those 2 colons next to each other. And then every grouping we had a leading zero, we've eliminated that. So 0333 becomes 333. 0044 becomes 44, and 0005 becomes 5. So this is a lot simpler. It does shrink these down, and that's going to help a little bit. I'm not going to say it helps a lot, because these still aren't that much easier to remember or write down like a normal IPv4 address. That said, that's probably one of the bigger things actually hurting the adoption of IPv6 in corporate networks, is the addresses are a bit of a bear to manage, and that a lot of folks won't acknowledge that that's necessarily the problem, but people just, network admins, network engineers, just don't want to try to remember these things and have to write them down and deal with them all the time. So that's certainly at least a factor in slowing down the adoption of IPv6. Now, with IPv6, we still have the concept of subnet. So that's important to consider, is that an IPv6 address, just like an IPv4 address, is divided into a network and host portion. Now, they actually have different names here. So the network portion is often called the network prefix, which identifies the network the host belongs to. And the host portion is called the host identifier, which identifies the host uniquely on the network. And it actually does that in a little bit more sophisticated of a way. Instead of actually being based upon just a randomly assigned number by the admin, it's actually based upon the MAC address of the interface that's connected to the network. And I'll show you exactly how that works here in just a minute, just a couple of slides. But it's important to know that you do have both a network and host portion on an IPv6 address. Now, with that said, IPv6 address structure actually varies a little bit based upon the type or purpose of the IPv6 address. And when I say type, I'm generally referring to unicast versus multicast. And actually, even within each of those groupings, there's a couple different types. So here in a second, we'll talk about unicast communication, which is by far the most common that you'll deal with, and the different types of unicast addresses that you'll see in relation to IPv6. So I want to start by talking about unicast addresses within IPv6 because unicast is generally the type of communication you're going to be seeing the most of. That means just like IPv4 or any other protocol, unicast means traffic from one host to another host, one source, one destination, talking back and forth with each other. Unicast one direction, unicast the other direction, so on and so forth. Now, there are two types of addresses we want to talk about here, and those are link local addresses and global addresses. So link local addresses are the first one, and that's really used when communication is intended for another device within the same network. A link local address can be identified by having its most significant 10 bits set such that the first grouping of the address, the prefix, is FE80. After that, the next 54 bits should all be set to zeros. Thus, you can spot a link local address pretty easily when the first half is what you see on the screen here, the prefix plus the padding, FE80, and then 3 groups of zeros, and that's how you know you're dealing with a link local address. Now, the second half of the link local IPv6 address is the interface ID portion, which uniquely identifies a network interface on an endpoint host. Now, on Ethernet networks, this generally can be based on the MAC address of the interface. And we have an example of that here. Now, keep in mind that a MAC address is only 48 bits, but you have to fill up a 64-bit space. So to do this, there's a little bit of a process that's involved. The MAC address is actually cut in half, and the value, the hex value FFFE, is added between each half as padding to create a unique identifier. There's also another step where the 7th bit of the first byte is actually inverted, so the bit is flipped either from a 0 to a 1 or a 1 to a 0. So that's a few steps, but the key thing to keep in mind here is that the interface identifier is based on the unique MAC address of the interface that address is actually bound to. So ideally, in that case, when we make the assumption that all MAC addresses should be globally unique, within a particular network, the link local address should also be unique because the interface identifier is based upon that unique MAC address. Now, the composition of an IPv6 address changes when it's used with global unicast traffic, and that's talking about traffic that's actually routed over the internet. So not just within a single network, but over across multiple networks. So when used in this manner, a global unicast address is identified by having its first 3 bits set to 001, followed by a 45-bit global routing prefix. Of course, on the screen you're looking at now, we have the network prefix all there together with the routing and prefix. You don't actually see the bit level, so you don't actually see those first 3 bits set to 001. But you do see the combination of those first 3 bits and the 45-bit, or in total 48-bit, global routing prefix. Now, the important thing to understand about the global routing prefix is that it's actually uniquely assigned to organizations by the Internet Assigned Numbers Authority, IANA. And it's used to uniquely identify that organization's IP space. So when you think about before how entire groups of IP addresses, global IP addresses, were assigned to organizations by IANA, with IPv6 unicast addresses, this is actually assigned, just our specific routing prefix is assigned. So it's not the entire address, it's just that routing prefix, and that's what you see here, which is a part of the global network prefix. Here. Now, the next 16 bits we'll see are the subnet ID, which can be used for hierarchical addressing, similar to the network mask portion of an IPv4 address. The same type of thing going on here. And the final 64 bits are used for the interface ID, just the same as the link local address. So that's the unique identifier for the interface that address is bound to. Now, keep in mind that the routing prefix and subnet ID can vary a little bit in size based upon how the network is subnetted and such. So that's something we have to consider as well. And you can look up specific values for that in the RFCs associated with IPv6. But these are the two address types. Basically, you really just want to be able to identify which one you're working with. Again, communication within a single network, you're going to be seeing link local addresses identified by FE80, followed by 3 groups of zeros. For global addresses, you'll see that those first 3 bits, when you're looking at them at the binary level, will be 001. But you also see that there's actually a valid routing network prefix here as opposed to groups of zeros. And when you see that, that's a global address which can be communicated with across the internet. So those are the 2 different types of IPv6 unicast addresses that you'll be encountering most often. So now that you understand a little bit about IPv6 addresses, I want to talk real briefly about normal stimulus and response. And it's not too much different than normal IPv4 stimulus and response. In this case, we have 2 systems that will be communicating with each other, System A and System B. In this case, they're using global addresses. So you notice that we start with 2001, and then we have DB8 and so on. So we do have those global addresses. They're not linked local addresses, and they're going to be communicating with each other. In this case, a packet is sent with a source IP address matching System A to a destination IP address matching System B, and that's one-way communication. IPv6 is not a reliable protocol, so that could be the end of it. We could just have one-way communication in that manner, but if it is indeed two-way communication, you would see a response wherein the addresses are inverted. So in this case, the response would have System B's address as the source IP address and System A's address as the destination IP address. And that's really very simple in its simplest form, IPv6 normal stimulus and response.